굳이 왜 나오는 건지 한번 설명을 네, 결국에 기울기는데
자, okay. We assigned homework, the task 4 yesterday, right? I'm gonna explain a little bit more about task 4. Okay, this is a very important task. Oops. Task 4. This is about a torsion. Torsion shaft in series. And today I'm going to assign task 5. Okay, this task 4 is due next week. Task 4 is due in 2 weeks. But depending on each groups, you can start task anytime. But okay, the task 4 is due next Tuesday. 날짜가 어떻게 되냐?
17일.
Okay, 17th November. October. Okay, I'm going to explain again about this task 4. Basically, many shafts are connected in series. And this is a shaft number 1 and shaft number 2 and so on, and shaft number n. Okay, number of n. Now, once you drive all the solutions and go to Excel, and you can specify number of n once you get the solutions. Okay, and each one you would have a polar moment of inertia. This let's call I1 and I2, I3, and so on. You have a IN. Okay. Again, left hand side is a fixed, and the right hand side also fixed. And each one has a length L1. L1 is this length, and L2, and 3, and so on, LN. And another one given is the radius, outside the radius. I will call R1, R2, and R3, and Rn. Okay, so these are all given. And now, how about a forces? First, we apply torque at each junction. And here, we apply torque 1 and torque here 2 and torque 3. And now, finally, here, we apply torque n or n minus 1.
N-1.
right, n minus 1. See, number of shaft is n, and junction, number of junction is n minus 1, right? So these are all given. Is it clear? Any missing information? Yes, there is one missing information, is a shear modulus. Shear modulus, G1 and G2 and G3 and so on, and you have a Gn. Okay, so these I will call given condition. Now, what to find? Okay, find is that I'm gonna draw here, and each junction, imagine we apply torque and torque and torque. Each junction we have rotation angle, right? And rotation angle and rotation angle, and then up to here, rotation angle n minus 1, right? N minus 1. So this one is that we need to find phi1 and phi2 and phi n minus 1. Okay? And another one is that inside this will twist and there will be shear stress, right? Shear stress, and this will be shear stress tau 1, tau 2, and 3, and tau n. Each rotor will have a same shear stress, right? Shear stress and shear stress and shear stress. So we will find a tau 1 and tau 2. I would say this is a tau 1, tau 2, and so on, and tau n of each shaft. Okay? So this is what we need to find. I'm going to give you a little hint how to solve this one. Hint. Let's take a look at the just one shaft. Just one shaft. And again, this is the a polar moment of inertia I and L and radius R and shear modulus G. Now, on the left-hand side and right-hand side, what we have learned is that angle phi is the torque T and L and G and I. You remember this, right? Right. Now, but be careful, what's the definition of a phi? Definition of a phi was that with respect to, we fix and then how much angle, right? So if we free to this one, you this rotate, right? So be careful, this phi is no longer phi. Say this is a phi1 and phi2, this will be phi2 minus phi1. Relative angles. Is it clear? Okay, it has to be relative angle. Now the tau, you know, tau is the torque, and I and times R. R is the maximum radius, right? Maximum radius. And to do so, you certainly need to have how much the torque T. Well, I would like to say as output, I forgot to say, output each shaft, you will have a torque T1 and T2 and torque Tn. Each one will have a certain torque, right? Okay. So this one is each torque and each IP and each R, the radius of R, and this is the tau. Of course, this is a maximum because the R is the radius, outside the radius. So this one is a all maximum. maximum, and maximum. Is it okay? Yes.
토크를 샤프트마다 걸리는 토크도 구해야 하는 거잖아요.
그렇죠.
근데 위에서 이 주어진 토크 값이랑 밑에서 구해야 되는 거랑 다른데 문자를 다른 걸 쓰는 게 어떨지.
이 T1이랑 이 T1이랑 다 같다? 헷갈린다? 그 얘기네? 네, 맞아요. 알아서 하세요. 네, 좋은 지적이에요. 여기가 지금 T1인데 여기다 대고 여기서부터 여기까지는 T1이라고 하면 안 되죠. 이게 사실 T1으로 하고 그러면 이렇게 바꿀게요. 이놈을 그러니까 중간이니까 T1, 2라고 하고 이놈을 T2, 3로 하고 이놈을 T3, 4. 그러니까 토크 가하는 건 이 중간 사이에다가 가하는 겁니다. 그렇지만 여러분들이 찾아야 되는 거는 what you need to find is talk from here to there. 근데 이게 you may wonder what is talk here and talk here, then what will be the talk inside? That is the one of the critical point in this problem. Let me show you one example. Very simple one. It's a two bar. This is L and EA and L2 and EA2 and A2. Now, when we apply certain force, say this is a P, see, there is a reaction force, and there is a reaction force, and there will be from here to there. See, this P, I will call P1, 2. This is a P1, and this is a P2, right? So, how many reaction force we have? We have a two reaction force. This is R1 and R2. Reaction force, but equilibrium wise only one equation, right? So this is a statically indeterminate problem. So anyhow, but what we know is that this angle of rotation and this angle of rotation has to be rotate the same amount, right? Same amount, and considering that we would have a same number of equations to solve, and the number of given and number of unknown, they will be the same. But I just want to say this is the typical case of a statically indeterminate, because a torque equilibrium is only one, right? Because all torque is here, 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 here is always only one equilibrium. But reaction is here, reaction is there. So two reactions and one equilibrium equation, so it's a statically indeterminate. Now, to solve the statically indeterminate problem, what do you need to do? Well, you have to consider each one material properties, and each junction, you have to have a deformation compatibility, right? So, I would suggest that you start with phi 0, okay, and phi 1 and phi 2 and so on, and this will be phi n, right? These are all unknown, but phi 0 is given as a 0, is a fixed, and phi n is given as a 0. Now each one would have this much relative angle of rotation, which is related to a TLGI, right? So you would have a series of equations. For this, you have this equation. This one, you have a P1, P2 equation. You have how many equations you would have? You would have a number of n equations, right? Okay. Well, it's more fun for you to solve yourself. I don't want to give you too much information. If I do, it's no fun for you, right? So, any questions? Okay, so this is a task 4, and now I will say task 5. This is a due in 2 weeks. But the reason I assigned this much earlier is that you can start to talk, okay, within your group. Well, you can submit anytime, I mean, even before 2 weeks, anytime. Earlier is okay. Here we have a beam. It's a beam, not shaft. It's a beam, and we apply P1 at a distance x1, and P2 apply x2, and we have a Pn at positions xn. This old shaft is a constant. Well, we could have this cross section is changing, but it will be too complicated. Just keep all cross sections the same, so that EI will be the same, is a beam, and total length will be L. And now this is a given. All the material property, all the forces, all the geometric condition here and there. And now this will deflect, right? Or deflect at the bottom, at the center line, will deflect like that. And this one we call V. It's a function of x. X is here. So deflection is the one we need to find. And I'm sure you already learned about beam theory in strength material 1. But today I'm going to review all the beam theory, but not in detail, but just overview. But this will be your another task. So to find a V deflection is a function of x. That's it. And hint is that we use the governing equations, which is the EI V is deflection. 1, 2, 3, 4 function of x is given function of distributed load qx. You learned this equation, right? Okay. So using this one, Gabon equation and boundary condition. What is the boundary condition? At x equals 0, here, x equals 0, we have a deflection is 0, right? Deflection is 0. And what else? Slope is 0, right? Slope is a slope has to be 0. So slope is a prime. And at x equal L, same thing, v equals 0 and slope equals 0. So this is the Gabon equation, and Gabon equation means that this is include all equilibrium equations and material properties. All you need to assign is this geometric condition, which is a boundary condition. So mathematically, this is the fourth order differential equations, and with the 4 boundary condition, 1, 2, 3, 1, 2, 4 boundary condition. Now, the key point is that Qx, this P1 and P2, these has to be given as Qx. So that P is a concentrated load. So P1 x minus x1. This is it's called singularity functions. And minus P2 and x2 and minus 2 and so on. Now, when you solve this one, looks complicated, but very simply, what you can do is just solve only, consider only one load. That's all you need to have. Only consider one load, this position, okay? This one, put it here, and boundary condition, you solve this one, okay? And which I will call V1. So this will be the only, this one will cause some V1, and this, so this will be a V1, and P2 will cause another one, which we'll call a V2. So V1, V2, and so on, this is a total V, and that will be the solutions. So all you need to do is just solve this one and given this one. So given will be P1 and X1, and you got the V1. And then you just change this, change that, you sum all displacement. Okay? How to add using Excel? In Excel, you would have X1, P1, and V1, right? You just copy and change P1 and X2, and you get the same equation, and you finally add all the displacement. Is okay? Yes. Please remember what I said. It's called superpositions. Just solve Q1 and get the V1. And so this will be P1. This solution will be P2, and so on. This is a solution for the Pn. So all you need to do is just solve one and just change the value and then add them. You may not understand what I'm saying exactly, but when you do that, you would understand what you just review my explanation, and you will understand better. Okay, so this is a task number 5, which is due in 2 weeks, and then we're gonna have a midterm. Okay, but again, this is the most important the problems. And now today I'm gonna spend time about the 1 hour to review all the beam theory you need to have. Okay, to be able to solve this one. Okay, keep that in mind. What we like to solve, drive, is this carbonication. How do we drive this carbonication? How we use this boundary condition and QX, well, you will study yourself, but the main point is this: how do we drive these carbonications? Just understanding once, and that's enough. And so the topic we will cover today is called beam theory. Okay, so beam theory consists of chapter 11 and chapter 10. Chapter 10 is about the basic deformation of the beam. So it's the beam theory 1 is the chapter 10, and chapter 11 is the equilibrium equation, and which will give us that carbonic equations. Okay, so beam, well, this is just another definition of a beam. Beam simply is a bending structure under a vertical load, and this this one-dimensional structure will bend, and is called a beam structures, mainly vertical load. So we have a certain cross sections. Any one-dimensional cross section, we have 3 forces and 3 moments. Now this one is axial force, which will be related to a bar, right? So this will call Fx. This is, say, x coordinate, and this will be Fy and Fz, and this will moment called moment x, which is happen to be torque, right? Which will be which is related to a shaft, and moment y and moment z. Okay, so this one is a bar and this one is a shaft. Now these 2 forces, this one and that, is all about bending. Okay, bending. And now we're gonna focus on system, and only this this is a force. Okay, we're gonna consider that vertical or downward force, and which will relate to a moment. See, this is a beam, and either vertical or bending. See my finger directions, this way or that way, moment, right? So y directional force and z directional moment, they are related. Okay, I'm going to explain. This one is a y directional force, right? And now moment-wise, so finger goes like that, moment goes like that. So this is a y force, moment is a z moment, right? Y and z. Now, if we apply force z, moment will be y. So it's work like a pair. So F, Y, and F force Z and this one. So we're gonna just focus on this one. Same story, same will apply to this set. So we don't have to worry, just let's focus on these two, okay? Now, first of all, before we consider force, let's consider only moment, okay? Only moment. And moment will be caused by force and from considering equilibrium, that we'll consider later. But let's say we have a beam and we apply only moment, or this one. Well, when we apply this, certainly we have a reaction force like that, okay? Only this one. And imagine what happened. And look at my arm, if we bend like that. This is a torque, right? This is a torque, and this extension is a bar, torque, bending, right? That's all your arm can do. This is twisting and tension and bending, right? Well, you can bend like that, but this is the main bending. So it's important to consider your arm as structures. See, tension and twisting and bending. That's how you exercise to strengthen your muscle. But today we focus on bending. Now imagine bending as in torsion. We always start with observing deformation. You remember that deformations? You know the deformations? You remember that line? That line is moved this way, right? So we start with deformation in bending as well. So let's take a look at the deformation. Deformation-wise, if you consider bending, and the top and bottom is simply this one is under compression, right? Compression, and the bottom is in tension. So that is a very simple observation, but very important. So when you bend, you have a compression, and this one is a bending, I mean the tension. So I'm gonna yes, you have to really pay attention, and bending is the most important and not straightforward. So I really want you to be careful. See, I'm trying to start with simple bar, and what is the difference between bar and bending? Okay, in case of a bar, as you know, all the deformation is something like this way, right? This much. So simply you can say this is the L, and this is a delta, and strain X is simply delta over L, right? This was a case of a bar. Very simple. But how about the bending? Okay, bending, rather than this force, now we apply this moment. Now, how about the deformations? That is very important. Deformation-wise, now this top, I mean, this one is tension, and uniform. But under bending, this top is a shrink. I mean, with respect, this we fix. Okay, for example, we fix. Then this one is compressions. And how about this bottom? Well, same as here. So we have a tension and compressions. So look at that. This is the all uniform, but look at that. This is the compression and tension. That is the biggest difference between bar and beam. So this is the epsilon x. Well, this is the x and this is y. And this is x and this is y. And as you can see, epsilon x was a uniform, just constant. But epsilon x is now, you can see, proportional to y. Proportional to y. So top is a minus, bottom is the plus. So let's just call minus constant y, which means that positive y will have a minus and negative and will have a positive, right? So important is the, that is the proportional to y. Is okay? Yes, that will give us a sum where on the top is a minus and bottom is the plus. That means somewhere we have y equals 0. There have a no strain, 0 strain. Means that this line does not extend, does not contract. There should be somewhere. So positioning, this is called neutral axis. And this one in the bar, we don't have any neutral axis. They are equally expanded. But beam, you have this way. Okay, you have this way and this neutral axis. Okay, this is the most important observations, deformations. Now, I'm going to go in a little bit more about this one. I'm going to use, with respect on the left-hand side, and this one was the before deformations. Okay, before deformation. Now, this one will rotate, and rotate will goes up and goes up like that, and here. And this is the important observation. So this line was the no extension, no contraction. So this will be a, we call y equals 0, and this will be epsilon x will be 0. Now is a linearly compressed and tension, and epsilon x is minus ky. But look at that, if this one, when we bend, this center of, there will be a angle change. I will call this is a theta, and from here to there. Okay, this is r. And this r, if we look at this this is a d theta. R d theta is what? R d theta is this much length, right? This much length is the same as a dx. So 1 over r is nothing but d theta dx. And 1 over r is in fact this same as this k. So k is a curvature. So r when it flat, how much is the r? infinite, right? Infinite. But when it bends, I'll get smaller and smaller, right? Which means curvature is increasing. So we don't want to say R is decreasing. We rather want to say K is increasing. So this is all same, has the same meaning. 1 over R or curvature or d theta dx, they are all same physical meaning. Okay? Please remember this is the, I like to explain very in a simple way. Okay? I think this is the simplest way. There's one more step. One more thing is that, what is a theta? What is a theta? Theta is this one. If we have a tangent, see what we like to find is this is what? This is a deflection, right? This is basically what we like to find. Deflection as a function of x. So this is a v. So if we have a tangent, and what will be this one? See, this one is theta, tangent, this is a right angle, so this will be the theta. So tangent theta is basically v derivative, right? Is okay? So if this is a small, this is a very small, and I cannot say less than 1, small, then this will be same as tangent theta. When theta is a small, tangent theta will be just a theta, right? Yes, sine theta, but sine theta is a theta, and cosine theta equal 1. So tangent theta, theta equals small, will be just a theta. Okay? It's not complicated, okay? Now, let's say, let's put this equation. This is the important one. So since we have a theta, let's put it here. Now, what do we have? We have K, or 1 over R. Okay. Now, this guy will be, K will be what? We put it here, we have a V second derivative, right? So simply V double prime. That is the curvature. This is the most important result, is that if we have a deflection curve, V in terms of x, if we have a second derivative, what is that? That is the curvature. What is a curvature? It's a 1 over R. Okay, so please remember this one is the minus K, okay, K, just keep these relations, okay? This one, what we know is actually moment is all we know, right? Moment is the force we apply, but we don't know how much curvature, we don't know how much this theta, right? So that we like to find. So input is K, moment, and what we like to find is K. K is unknown. Curvature is unknown. We don't know how much it bends. Similar to this, let's take a look at the shaft. When we apply the torque, we don't know how much it rotates, right? So, but that will be the result. So in this case, is the same thing. the rotation or curvature will be the output. Okay. I'm trying to put all equations inside, in this one slide. See, once we have this this is the deformation condition. Now stress equal E epsilon. Remember, we have a stress-strain relations, and this will be what? Sigma equal E ky. So this is a deformation condition, deformation observation, and this is the stress-strain relation. You remember from bottom to top, right? Deformation, strain, and stress, and then what? What's the last step? Equilibrium. Yes, equilibrium. Equilibrium means that when we have a moment, if we look at these cross sections, the stress distributions, say this is the sigma, this is a stress, and sigma times A will be the force. So sigma times dA will be the force, and what do we need to multiply to get the moment? Distance, right? So what's the distance? Y coordinate. So Y is the moment. So this is the equilibrium. See, this is the equilibrium, and this is the stress strain, and this is the displacement. So you put it here. Now see, what do we have? And E and K, all constant. Okay, I'm sorry, there's a minus there. And E and K, and what left is the Y and Y. There will be Y square dA. What is it called? Moment of inertia. Yes, that is the moment of inertia. I will call B, bending, moment of inertia. So simply, we have moment equal E I K. Okay, K I'll put the last. E I K. E I K. So this is the one last result we have obtained from all these consideration. Consideration means displacement and stress strain and equilibrium, and this is the what we get. Remember what is the K? What is the K? K was d theta dx. Remember this theta? Okay, so I will write down here. Moment equal EI curvature. Curvature is a d theta dx. So if this is a fixed and this final will, if is a theta 0, will be theta 0 divided by what? L. That is a d theta dx, right? So here, what will be the theta 0? Moment L E I. Do you remember these equations? When we have a shaft and length, polar moment of inertia, and length L, when you apply torque T, how much it rotate? Torque T, L divided by G, I, P, right? Exactly same. Force, length, and material property, E instead of G. Instead of IP, polar moment of inertia, we have a bending moment of inertia. Right? Okay. So this is a first step of a beam theory. There is a second step, which I will explain, but this is the first step. And I will summarize here. Okay. Summarize bar and summarize the shaft and summarize beam. Beam is like that, and it will rotate how much the angle theta and shaft and torque, and how much it rotate the theta, and bar you apply the force and how much it extend the delta. So delta, or this we call phi, angle, and this is the angle of rotations. And cross section in the bar you have A. Beam shaft you have a polar moment of inertia, and bending you have a bending moment of inertia. So in the force you have a F, and you have a twisting moment, and you have a bending moment. Now cross-sectional property, you have A and polar moment of inertia and bending moment of inertia. Now, deformation-wise, you have a delta, is a force, length, cross-sections, material properties. And shaft, very same, similar to this, a torque is a force, and length, and material property, and cross-sectional property, which in this case IP. And bending, we have a moment, length, material property. You can see that you have a exactly same stress. This is a force divided by A, and shaft, we have a torque divided by IP times R. And bending, we have a moment, IP, and Y instead of R. As you can see that all three structures has pretty much the same similarity, so you can understand them all together. Okay, so that is the first part of this now, chapter 11. Chapter 11 is the all about equilibrium. What is the equilibrium? In the beam case, okay, in the shaft, how many equilibrium do we have? Torsion, you only have one equilibrium, right? Only this one equilibrium. But in case of a beam, we have a beam, vertical forces, we have a two equilibrium. One is the force equilibrium in the y direction. And what is the second equilibrium? Moment equilibrium, right? So y force and z moment. So we have a two equilibrium. That makes beam little more complicated than torsion. So we have a y directional force and moment equilibrium. So we have all the forces, these forces qx, and sometimes concentrate a lot. Sometimes we have a reaction force, and sometimes we have a reactions and moment. And simple support only have a R, but clamped we have a moment and force. So two equilibrium, and how many unknowns can we solve? Only two unknown, which means that sometimes statically determinate, sometimes statically indeterminate. But anyhow, the main point is the two equilibrium. These two equilibrium, I will combine them. See, remember, chapter 11 is all about beam equilibrium. We have a two equilibrium. One is the y-directional force equilibrium, and second is the moment, z-directional moment equilibrium. Now, you have a certain small regions and where we have a distributed load, and on the left-hand side, we have a moment, and the right-hand side, moment and shear force, but there will be some increment. So considering equilibrium on this part, corresponding to a length dx, we have this result, and moment equilibrium, this result. Well, you can go through, but let's skip that. This is the result. So it tells that cross-section V, rate of this change is equal to a Q, and so on. Here is a V, and V, we put it here, and second derivative of moment will be the Q. This is the moment equilibrium. So this is a given is a Q, and in certain cross-section, we have a moment. Moment, second derivative is always Q. This is a moment equilibrium. I mean, force equilibrium, okay? Now, last step. Last step. See, moment and curvature, this was a chapter 10. Moment curvature relation was a moment equal EI curvature. But curvature, we just observe that EI, what? V, second derivative. See, again, this is the curve, and this is the Vx. And so V second derivative curvature, and this is a function of x, and this is the function of x. This is all about the chapter 10. Now, chapter 11 was the equilibrium. Two equilibrium, put them together, what do we have? So equilibrium, we had moment second derivative will be Q. Now, we put this thing into here. We will combine chapter 10 plus chapter 11, and what do we have? Just a second derivative will be EI, two more derivative will be QX. So this is the Gaboni equation, which governs, say, this is the beam. We have QX, function of X, distributed load, and each cross-section is the X, and each one we have a moment. I'm sorry. X, we have a deflection, I will use different color, deflection, and this will be the function of x. So given qx, and output will v as a function of x. So forget about the old beam theory. Now we have differential equations. Not complicate, just a simple first order differential equations. All you need to do is just integrate left and right. You can integrate, right? And then integrate one more time until you get just a v. When you integrate, you will have a constant, right? And another constant. How many constants you will have? Since this is a first differential equation, you will have 4 integration constants. So 4 constants. Now, how do we calculate or determine these 4 integration constants? Yes, exactly, boundary condition. So how many boundary conditions do we need? Yes, we need a 4 boundary condition. So always on the left-hand side, we have a 2 boundary condition. On the right-hand side, 2 boundary condition. Always. For example, if it is a clamped and free, clamped, what does it mean? Oh, V equals 0, right? And deflection equals 0. I mean, slope and deflection. And if it is a free, means that here, moment equals 0 and shear force is 0. Moment 0, what does it mean? Moment 0 means second derivative is 0. And V, shear force is 0. What does it mean? Third derivative is 0. So always, whatever boundary condition you have, we have always a 2 on left, 2 on the right. So total 4, and using this total 4 integration and boundary condition, we determine these 4 integration constant. Then we can complete V. X. So what is the given? Given is this guy, Qx. Any point you like, have force, and you can integrate, and using 4 boundary condition, you can have it, right? Okay, so this is all I'd like to say today. And back to our problem. I mean okay, let's get back to our task number 5, right? Now you understand this is the bound governing EI, V 4 times, and QX, and boundary condition. In this case, a deflection 0 and slope 0. On the right-hand side, deflection 0 and slope 0. So 4 constant. So when you solve this one, you would have a 4 integration constant, which will be determined from this. But now what you need to do is this represent Q in terms of P1. Q is the distributed load. P is a concentrated load. That's why we have a singularity function. You can go and you can get more a little idea about the singularity function, not so difficult. And okay, so that's all about the beam theory. Again, chapter 10 is all about displacement, strain, stress, and moment equilibrium. In this case, moment equilibrium is integration sigma y dA. And from that, what you get? We get moment equal EI curvature. That is the result of chapter 10. chapter 11, we have a 2 equilibrium for the beam and 2 equilibrium combining. Second derivative of moment equal Q. Now, chapter 10, chapter 11 merge, we have a fourth order differential equation. So given loading is Q, and you can just integrate 4 times, and you will get the deflections. So basically, you can solve any beam theory, any beam problems. Okay? Again, why this is so important? Well, as we reviewed yesterday, when we design the wing, okay, let's say you design of an airplane. Now, the most important structure of an airplane is, of course, this wing. Okay, this wing. And wing, a cross-section has to have a certain airfoil. You know what I mean, airfoil? Airfoil is that when we have some wind, air flow, and this air will travel, and upper we call suction side, and down we call pressure side. And suction side, the speed is really high, higher than bottom, so pressure is low and pressure is high. So there will be certain pressure distributions. And this will cause a bending moment. So each cross section, okay, here, you have a cross sections and cross sections and cross section and cross sections, and each one you need to calculate EI. And EI, and this is a QX. So all you need to do is to solve EI and V 4 times and QX. Well, EI is changing, so actually we have to derivative EI as well, but just for the purpose of simplicity, I just use EI and Q, V 4 times and QX. There's a boundary condition, and here we have a fixed. So we can say V equals 0, V prime equals 0, and here is the force is 0 and moment is 0. Again, two boundary condition. We have a 4, and we can solve this one. Actually, when they design in Boeing and Airbus, they really use this equation as a force approximation. This force approximation is give us about 90% of all real airplane behavior. So you understand how important the beam theory you have. This is a very typical application, but imagine you design as a bridges, right? Bridges and all the load, and you can again design a bridges or automotive and basically all structures. So most of the structures, even say this a fuselage, okay? This is considered as a beam as well. All the load and how much it deflects and how much stress will have. Okay, any questions? So as I announced, you go through, of course, this is the, this semester is a strength of material 2, which means that we you have a class in advance, strength of material 1, but I just review all torsion theory and beam theory for you, but my review was not, of course, complete. I didn't cover completely. You have to go through and you have to study yourself. And here, of course, you, as a group, you work together and have a PowerPoint and using Excel. And here, same thing, you have a PowerPoint and you have an Excel and you co-authored and work together. And then from this task 4, you would have a 10-minute video and upload to YouTube. Okay? So next week, we will review your video, each group in class, and watch it. Okay? So next week, we will have a just watching movies. Okay? I hope we can enjoy. You are all directors and producers. I'm gonna just watching movies. Okay? And at the same time, you keep discussing about these beam problems. Okay? But this one, you have to start to solve now. And one thing I didn't mention here is that if we pick this part, okay, which means that this is a very important equilibrium, and just here, and imagine that here we have, for example, torque T, let's say T I, let's say torque T J, and at the middle, at the junction, we apply what? Torque T IJ. That's our definition, right? So if we consider equilibrium only this part, what do we have? We have torque equilibrium will be Tij plus Tj minus Ti equals 0. Okay, so Tij is all given at each junctions. And Ti, Tj is the unknown you need to solve, right? I'm trying to help you to formulate. As I mentioned, P1 and P2 will be used to calculate this, how much, the angle of rotations and torque of each one. So, this is I hope that help you to solve the problem. See, this one is not so important. Why? Once you have a torque T, tau is simply what? T, I, and R. So don't confused by this guy. This can be solved at the last moment as a post-processing, right? Or you need to find a phi and T all together. Equilibrium equations, and this is what? Force and deformation condition, and deformation boundary condition. See, even this one, we have a force, torque, and equilibrium. In this case, only one equation. And material property, in this case, we have N material properties. And geometric condition, we have a here, we have fixed, and here we have to rotate together and together and together. But if you fix, you define P1 and P2, which is okay, because we only defined only one value, which means that at each junction it rotates together. Okay? So I hope this my further explanation will help you to reduce all derivations. Okay, this is all I'd like to mention today. Any questions? So how about the number of n? Well, it's up to you. You choose. You can choose number of equations in Excel. You have to choose, right? In Excel, you can choose number of equations n equal 4 and 5. Or if you can choose n. I mean 10 or 100. It's up to you. But you remember the last time you have to inverse this matrix. I'm sure this one will have some kind of a coupled linear system. F equal kx. I'm sure about that one. So if you have a 10 shaft, it will be 10 by 10 equation you have to inverse. But thanks to Excel, M inverse, you can easily, numerically, right? So don't choose 2, don't choose 3, choose more than 3, okay? And 4 or 5, wow, 100 will be welcome. No problem, just enter. Excel, you know how many cells they have? Millions. So if you choose millions, I don't mind. Okay, any other questions? So remember to make a nice movie, and let's hope to enjoy watching movie. Okay, thank you.
The top should like